Hello, everyone. My name is Huang. I'm a relatively new postdoc here at Santa Cruz, and I have just moved from University of Tokyo, Cavalier PMU. I have been working with the team for the Subaru Suprime-Cam survey for the last couple of years, and I'm here to tell you the story about the example of the most massive galaxy in the universe. So today I'm going to talk about basically these are the population of the most massive galaxies that have stellar mass more than 10 to the 11.5 or 11.6 solar mass. They are the central galaxy of the most massive dark matter halo in the universe. And in the nearby universe, most of these galaxies are quiescent and early type looking, basically massive dipole galaxies. I'm sure it looks boring to some of you. Since this is a conference with a very broad topic, just to draw your attention to this object, their progenitors are very likely to be the high redshift luminous quasars or the protoclusters you're looking into. Thanks to the observation and simulations happened in the last decade that many of you here have contributed to, I have some confidence to summarize this picture into a very oversimplified cartoon. So about the assembly of this massive galaxy, right now we can very broadly separate them into the so-called two phases. In the first one, at high redshift, the dissipative process, intense dissipative process built up a very dense stellar core of these galaxies. And after star formation has been quenched by certain physical process, the second phase ensemble is largely dominated by accretion of smaller galaxies. So as a result of this picture, in the nearby universe, if you look at a massive galaxies, if you look at the inner region and outer region, they're actually dominated by stars that form in different halos and have different assembly history. This is a very promising picture, but still have many problems, and some of them even very fundamental. For example, although this galaxy may look simple, they have been proved to be very hard to model, and hence it's actually not that easy to define their total stellar mass, largely thanks to their very diffuse and very large outskirt. And because of the dynamical timescale in the outskirt are actually very long, and most of the outskirt are actually kept the important information about their recent assembly, we really want to know how their stellar halo depend on their total stellar mass. And one step further is how the structure depend on the environment. Right now, the difficulty to answer these questions partly is because of the limitation of the data. That's where the HIC survey can help. So I will not bother you with a lot of details about the survey. So basically, this is a very ambitious cosmology survey using the new prime focus camera on board of the 8.2 meter Subaru telescope. Instead of showing all the details, I will just show you this, basically one corner of the universe imaged by this camera. And in case you do care about the details, here's some key information I want you to know. So this is a 5-band survey, and will eventually, in 5 years, cover 1,400 square degrees of sky. Relevant to this work, these images, especially in the I-band, have superb seeing. Our median seeing is 0.6 arc-second. And these images are extremely deep. So even in the wide field, the so-called HIC wide field, its point source detection limit in I-band is approaching 26.5 magnitude. And we do care about the surface brand limits, which again in I-band, we can easily reach down to 28.5 magnitude per arc-second. And right now, we are not limited by the signal ratio. We're limited by accuracy of background subtraction. The massive galaxy I'm talking about mostly look like this. And I want to quickly show you why HIC is particularly useful for this type of galaxies. So this is, again, let me first say this first. This is a completely unfair comparison. So this is the three BCGs in the nearby massive clusters imaged by SDSS of 2.5 meter telescope. And this is what they look like from the HIC 8.2 meter telescope. As you can see, although the SDSS image is not that bad, all these galaxies have well resolved. The HIC image can show much more detail in the outskirt and help us trace their stellar mass distribution out to 100 and even for 100 kiloparsec even further away. And this is extremely, this is extremely useful for our topic. And right now, we are only focusing on the nearby, the massive galaxy in the nearby universe, where the current HI survey already provide us a volume to explore the galaxy at a very high mass end. And we only care about the galaxy with reliable spectroscopy redshift. And we have already gathered a large sample of these galaxies. We perform 5-band acid fitting to derive their mass-light ratio, and we do our own careful photometry to extract their 1D stellar mass distributions. And before that, we even try to empirically correct the background subtraction and aggressively mask out all their surrounding satellites of foreground galaxies. So this is an example of the 1D profile we can extract. So I want to draw your attention to, this is the physical scale, and the x-axis here actually in R to the 1/4, because the elliptical galaxy typically look like a straight line on this coordinate. And we, using a different way to extract this 1D profile, we explore the impact of PSF and the background subtraction. So right now we conservatively mask out the inner 6 kiloparsec because it's affected by the PSF convolution. And we basically stop our analysis at 100 kiloparsec to make sure that this profile is not affected by the background subtraction. And this information can tell us the 1D stellar mass distribution, and we can also integrate this profile to get the stellar mass out to very large radii. So the first result come out of our research is that HIC, the deep image, help us recover more flux. If you have used SDSS or other survey before, if you want to study this massive galaxy, you're probably using something like the C-model photometry, the Walker photometry, or single source photometry. If you have done that, you have a sample, you plot their volume the stellar mass volume density distribution of these massive galaxies. What you have is something like this. This actually is based on the HIC C-model magnitude. The mass actually is incomplete. Now treat this like a stellar mass function. But if you replace the stellar mass here using the mass integrated out to 100 kiloparsec, you get something like this. So you can see basically the stellar mass function, stellar mass density distribution at high mass end has a. This is even without changing any assumption in the stellar population model. This is just because of photometry. So as many of you know much better than me, the stellar mass function at a high mass end have great physical implication, and such this difference should be carefully taken into account. And as I just showed, so we take the 100 kiloparsec radii because of a technical limitation. The stellar mass distribution doesn't stop there. So actually, if you keep increasing the integration radii, you can further change the shape or the normalization of the stellar mass function at a very high mass end. Now move away from this, just the stellar mass we get from the 1D profile. Let's look at the profile themselves. So here I show the stellar mass density profile for a large sample of massive galaxies, and I separate them into the 3 stellar mass bin using the mass within the 100 kiloparsec. And the different thick line here show their median stellar mass distribution. And here we see an interesting result is that the stellar halo of the massive galaxies are not self-similar and clearly depend on their total stellar mass. Their inner stellar mass density profile, the slope are very similar, but in the outskirt, they show large difference and a lot of scatter. As I should emphasize here, because of the depth of the HSA images, the scatter we're talking about here are not because of photometric error. This is intrinsic and has interesting physicals inside. Besides this, the 1D stellar mass density profile, we can also extract the shape of the stellar mass halos in 1D. And here I show the ellipticity profile of the galaxies out to 50 or 60 kiloparsec for the same sample of massive galaxy in the 3 mass bins. And again, I show their median ellipticity profile. So here the interesting result is that not only the stellar mass density profile depend on their stellar mass, the average shape of the halo also depends on stellar mass. The more massive you are, the more elliptical your stellar halo becomes. And again, I should emphasize here, so we are not using any stacking. So any scatter and the trend here are not limited by the stacking technique. So now let's move away from the stellar mass dependence. Let's move to the next topic, which is environmental dependence. So right now, it's not realistic to derive halo mass for each individual of these massive galaxies. But thanks to the Red Mapper cluster catalog, which is a very successful red sequence cluster finder, we can find a large sample of massive clusters at low redshift. And we can take their central galaxies, or so-called BCGs, as a sample of centrals in very massive halos. And this sample can also help us remove the massive satellite galaxy in these massive halos. And in the same spectroscopy sample, all the other really massive galaxies that are not within any of these node clusters, we basically treat them as the central galaxies in less massive halos. And now we'd like to compare their stellar mass distributions between these two samples. And before that, I'd like to draw your attention to these two very important physical scales. So in simulations, it's actually very straightforward to separate the stellar mass of a massive galaxy into the axial or the accreted stars and in situ stars. And as you can see here, they often occupy pretty different physical scale. However, in observation, we do not have the luxury to do that easily. So in this work, I make some assumption. So based on, so right now, we basically assume that the stellar mass within the inner 10 kiloparsec is a proxy of the mass formed as the in situ component at a high redshift. And we use the mass within 100 kiloparsec as a proxy of the total stellar mass. As I just showed, this mass was shown to provide a much better estimate of the total stellar mass than the traditional model. Here is a figure that demonstrates the diversity of stellar mass structures for massive galaxies that are defined by these two parameters. So from top left to bottom right, all these galaxies share very similar mass within 10 kiloparsec. And as you can see, their total stellar mass keep increasing from here to here. And the three red boxes highlight the three BCGs. And this diversity is, again, very interesting. Now, I'll show that from the 1D profile perspective. Now, if we match these two samples of central galaxy from different halo mass at the fixed stellar mass within 10 kiloparsec, which again is a proxy of the in situ mass, you can see there their average, the distribution of their stellar mass density profile and the average profile are dramatically different. Although their stellar mass profile are very similar within 10 kiloparsec, the central galaxies from higher mass halos possess a much more prominent outer envelope. And the difference here is very significant. This is, if you, again, you assume that the mass within 10 kiloparsec treats the in situ from in situ mass, just tell you that the galaxy forms similar of stellar mass in the first phase, actually accreted very different amount of stellar mass in the second phase, and depending on their halo mass. If you match these two samples at the stellar mass within, again, 100 kiloparsec, you can still see a more subtle, but still statistically significant difference, which indicate the stellar mass distributions of these massive galaxies depend on their halo mass, or if you like, environment. And this difference, actually, you can view it from the scaling relation angle, which here I show the stellar mass size relation is the focus of many previous research. And the previous research about the environmental dependence of this relation often result in non-detection or sometimes confusing result. Here, again, I plot the mass within 100 kiloparsec with the R50 derived from the 1D profile. Our massive galaxies show basically lie on this very tight stellar mass size relation that are consistent with the literature. Meanwhile, we can say that these two samples, again, the red dots are from the central galaxy from more massive halos, and the gray ones are the central galaxy of less massive halos, have different typical size at a fixed stellar mass. And they also follow the stellar mass size relations with similar slope but different normalization. Basically, at a fixed total stellar mass, the central galaxy from more massive halo are 20% larger in half-life radii. This is, again, this is interesting, but I'd like to point out that the definition of size is sometimes ambiguous and difficult to measure in different situations. So here we propose that actually you can just show the same trend using the mass within different aperture. So here again is the mass within 100 kiloparsec and the mass within 10 kiloparsec. Total stellar mass, proxy of in-situ mass. And so here we show again that it is two population, the two population of central galaxy from different halo mass actually follows different relations. At fixed total stellar mass, the central galaxies from more massive halos actually have a smaller fraction of mass within 10 kiloparsec, but meanwhile has a much more prominent stellar mass halo. The advantage of this is that because we only use stellar mass within different physical aperture, it can be easily used to compare with the simulation. Actually, the preliminary result we have done with the massive black hole simulation has shown that the same trend actually can also present in the simulations. So here is the main conclusions. Basically, the deep HIC photometry can greatly help us map the stellar mass distribution of the massive galaxies. And we have shown that we can recover more flux from the deep image and have better estimate of the total stellar mass. And we have conclusively shown that the stellar mass density distribution, the mass size relation, depend on not only their total stellar mass, but also the environment. And right now, what we see is roughly consistent with the prediction from the two-phase scenario. And there's more solid constraint we can extract from this. So the next step, we will try to provide more detailed comparison with the simulations, and we will try to take into the weak lensing analysis from HIC into consideration. And sorry, I'll just skip this. Thank you very much. Sorry.